So we're talking about, but actually also CMS is doing, LHC is doing more, so probably it's the same. So that's a lot of data that has to be processed. That's why once when I went to interview to a new job, and they told me that they're using a lot of data, and I said, me too. And at the end, what they're using is like few gigabytes. I was like, okay, this is not, this is like few events. So computing store the data from 100 interesting events per second, and that's 100, each event is about 1 megabyte, so basically 100 to 1,000 hertz. And this is where we're going from level 1 trigger to high level trigger. So we started with 40 megahertz, we went down to 100 kilohertz, and from 100 kilohertz we're going down to 100 to 1,000 hertz by actually a huge farm of computers. And the computer farm is taking this time not only the calorimeter but also the pixel. And we're taking all the event, we reconstruct it very fast. We have a pipeline, and things are done in parallel. Parallel just because there are many computers, everybody takes different events. They take all the information from the event, reconstruct an event, and do a very quick dirty physics, like really baby thing. Like this plus this should be opposite to each other or stuff like that. Interesting physics, puts in. And stuff that are not interesting are not recorded, only a control sample of them. So this is the level 1 trigger, level 2 trigger, muon system requirement. The identification of muons even at high luminosity is not particularly difficult with the muon detector. Since the muon is the main component of the trigger, the challenge here is to reliably the reliability of the detector as a whole. For the muon chamber, the purpose, again, the method was many detectors, layers, placed inside the return yoke and also outside. And the iron of the return yoke absorb all other particles. Only muons transfer the muon chamber. So the total area of the muon detector is the same as that of the soccer pitch, 6,000 meters square. This is the total area of the muon detectors if you spread it out. Okay, so let's go and complete the task. You know now approximately how to build your detector. You have some idea. And we're going to start putting it together. And you can see here, this is the hole. You can see the hole before CMS was put in. They dig the hole. It goes, I don't remember how much they have it, like 100 meters underground. The experiment is. You don't want any noise. Even though they figured out that even there's a lake close by, Lake Geneva, and effect from like Geud v'Shefel, how do you say, like tide and the tides. So effect from the tide you can see on the beam, or effect from the train, the high-speed train in Europe going by. You could see, we can see effect on the beam. It's amazing. I mean, this is just to tell you how precise the experiment is, that they could measure even periodicity that had to do with the train or with the tides and stuff like that. Okay, and you can see here the hole. This is again amazing mechanical engineering here, because the tolerance, I remember, was barely a centimeter to put stuff in, and they managed to, this is the way it was done, and it was done without any issue. And in 2006 they started taking the pieces of the detector down and assembling, you see, assembling piece by piece. We're entering here the electromagnetic calorimeter. It's all engineers at this point. Nobody lets any student build here, only expert here. And this one on the silicon, they're sitting on the silicon and putting the electromagnetic calorimeter in. And you can see all the huge amount of cables that is connected. The electronic is humongous. And this is the people, this is the head of the silicon tracker group. And they just made a joke. One silicon tracker, 10 million channel, some assembly required, right? So, and look at that, look at the hydraulic system, that's impressive here. Look how this is like, it looks like, but look, this is really going in like this. That was really amazing. And this is the detector, and I won't go now. The only thing I will mention to complete the picture of this detector is once the detector is done and closed, everything is beautiful and now collision will start, but how do I get the data? I can tell you that in parallel there is like a huge group of people, computer science, like people that, or physicists that work with, expert in computers, and all they do is like, where do I save the data? How do I make sure that all the worlds get the data? And you can see there is the tier 0 that is at CMS, at CERN. They have all the data. Everything is recorded, is there. But then it's distributed to tier 1s in few different places, not so many. And so there was a copy of the data at Fermilab, for example. There used to be an experiment, so they have a lot of experience. A copy was there, there's few copies. And then there's multiple tier 2, also not so many, multiple tier 2 that were like, you know, for everything that you do, there was a Monte Carlo as well, right, to test our understanding. So if you have million or billion of events, you also have to produce more Monte Carlo than data. How do you do that? So they had many universities joined these tier 2s, and they had farms that were all interconnected. So when I send a job, I don't know if my job ran at Princeton or in China. So I just send a job, I could look, I could see actually. I have few in Munich, few in Budapest, few in this. I could see where my jobs are, but that's what it was. It was like going by, and you can imagine you send 1,000 jobs and half of them fail, and you come back and there's like keep processing, and there's like non-stop processing. But all that is a different area that I won't talk about, that you can imagine. And there's the database and how you write things into the database and how you instantiate and all this stuff. This is like a huge, big other area, which is data workflow. That's it. Okay, so I hope you have a sense of the work that was required for this detector. And any question regarding this or regarding, let me see, how do I take it out? I just take it out? No. Yeah? Where's the eject? Here? No. Here?
Like the top corner.
Top?
Yeah.
Here?
Yeah. That's right. Removable disc.
Here?
Not on the side.
No?
All the way on the side.
Here?
Yeah.
Thank you. Okay. So, so the question is, I gave you homework, and I also gave you a project with list of talks, now papers. Now the idea is that, like, again, you pick one of them. If you feel like looking at other papers, you're more than welcome. You can go to the High Energy Archive online, and you can look at things. And I'm happy with anything. The idea is just so that, like, one time you kind of have the feeling of going through this, looking at the references, just to get a sense of what how it goes. Details of this paper. The more you know, the better. And you're supposed to give 10-minute talk. There will be a few questions. You can do a small write-up. I'm okay with that, either way. But the more important is a good talk for 10 minutes with some questions. So we'll do everybody at the same day. Yeah? Yes. Excellent.